the users to be able to run their own applications. We started by defining the process. The only idea I would like to emphasize here is that the process models an entire computer with all its hardware components. So in a process, we have everything a computer has, generally speaking. That's why we could call a process a kind of a virtual machine. So it's a virtualization concept. Another aspect we have to keep in mind all the time in relation with processes is that they provide isolation, which means a process must be isolated by one another, by the other process, which means that any resource allocated or the resources allocated to a process must be different, disjoint by the resources allocated to another process. We will mainly see that in terms of memory, but it's not the only resource which must be isolated from a process to another. Okay, I also explained you how a process memory is provided by the operating system, and I would make a brief review of this on a picture. So remember that every process sees the memory as the computer's memory, the entire computer's memory, as if that computer's memory belongs only to that process, which is not true, obviously. That's why we call the memory which is viewed by a process its virtual address space. Okay, so virtual memory address space, if you want to be complete. So starting from 0, going up to a maximum, and that's similar for every process. Okay. Physically, things obviously are different. Each process is allocated its own disjoint and different space in the physical memory. That's the way I name physical memory, the RAM. Here we also have the operating system, and then we have memory allocated to different processes. And the operating system, okay, illustrated in a logical way, okay, just to explain which is its purpose. So the operating system, which is the one deciding where to allocate physically space for every process, so know exactly where each process is physically, is the one preparing what I call generically memory mapping tables, or in terms of paging, page tables. So each process has its own memory mapping tables. That's of process P1, that's of process P2, which map the corresponding address space of that process on its physical allocated memory. But I also told you that in modern operating systems it's used to also map the operating system inside each process virtual address space. Otherwise, of course, we should illustrate the operating system also here as having its own virtual address space. But I told you that many operating systems, Linux, Windows, including your HAL, maps the operating system at one end, usually at the end of the process virtual address space. So here is where the OS is mapped in the virtual address space. Here is the part reserved for the process itself. And the memory mapping tables are also divided in two parts. The first part, which maps the process own memory, okay, like that. And the other part, which maps inside that process virtual address space the operating system. And that's similar for the second process, okay, like that. This other part goes or maps that OS. I told you the reason of having something like that. The reason is for helping the operating system when running its code, usually handling system call. Okay, that's the most common example and then the best for us. So when handling a system call in the context of the current process means that the CPU is configured to know which are the current memory mapping tables allocated to the current process it executes. That's because when we have the memory virtualized in that way, for instance, when we have paging activated, it's the CPU which must know about this. Actually, we say is the architecture providing the paging mechanism, okay? But let's say that the CPU must know about the virtualization of the memory, and is the CPU which translates from virtual addresses into the corresponding physical addresses, into their corresponding physical addresses using those mapping tables, okay? So when the CPU is instructed to run code in what we call the current process, it is configured to use some specific memory mapping tables. Those created, configured by the OS for that process, okay? And when such a process executes a system call, okay, and the CPU now starts running code inside the operating system, and such a system call provides a virtual address from the process address space, and the OS must use that address. I told you, I gave you the example with the read, being instructed to read from some file and then to store the read bytes, the 10 bytes was my example, to store them in a buffer. That buffer, okay, is inside the process virtual address space, and actually the OS is given such a virtual address, okay, which points to where the buffer is allocated in that process virtual address space. So the operating system usually cannot use such addresses as they are. Supposing that the operating system would have been created another virtual address space. In its own virtual address space, the OS, or for the OS, that value VAP1 would have been totally different, or could be mapped on a totally different physical address. But in our case, it must be mapped in the process one physical memory, okay? But having something like that, the OS inside the current process virtual address space, when the OS runs, the memory mapping tables remains the same. Anytime a virtual address inside the OS is given, is used by an instruction, okay, here in the OS code, the CPU translates that VA OS using those entries, those part of the memory mapping tables, which are mapped here, so correctly inside the OS. Anytime the OS uses a virtual address, which is in this part where the process one's memory is reserved, that VAP1, okay, let's take it this one, will be mapped using this part of the same memory mapping tables, okay, which are mapped correctly here, okay? So one reason of having this is to help the OS access the current process memory. The other alternative, if you remember from last time, would be for the OS to map inside its own address space. So to find the gap and to map there the I'm back. Finally, I had some problems with my connection to the internet. I hope that now you can listen. You can hear me again. Can you?
Yes.
Yes.
Okay. Thank you. Thank you. So. So I was here remembering you about our discussion, our ideas discussed last time actually. So I told you the reason of having the OS mapped inside each process virtual address space. I also told you that when we want to make access. So now supposing the CPU is running process P1, so the OS is mapped here, okay? So the OS is logically like that. Here is the RAM, here we have another process P2. And now if, for instance, you will encounter a situation like this, when the CPU is running that process and that process executes a syscall like create process or process create, doesn't matter exactly how it is called. And now the CPU is running code inside the OS handling that system call. The OS, okay, so the P1 is here, the OS is here, and now the OS must allocate physical memory for another process for P2, must prepare the paging tables, the memory mapping tables for P2, okay, such that them to map the user space part of the process P2's memory here and the OS part here. I will not illustrate that anymore to not complicate too much that picture. And now the OS is running in the context of P1. So the CPU is using the memory mapping tables of P1. And you have to make some preparations inside process P2, the child, okay, in our example. Like, for instance, you have to prepare is stack, is something that we'll talk about in more details immediately. So the OS is running, okay, in the context of this process, so it could easily make access to any memory of that process, any virtual memory of that process. But if the OS wants to make access to that memory, okay, in terms of virtual memory, sorry, okay, it cannot do that directly because that stack will be at the virtual address in process P2, but the OS is running in the context of P1. So the CPU is using these memory mapping tables. So for the OS running here to be able to make access to such a memory, which of course it could find out where it is physically. So these virtual addresses in the stack are mapped using memory mapping tables of P2 here, of physical addresses in P2. So the OS could inspect, okay, these tables to find out which are the physical addresses mapping the corresponding virtual addresses in P2. And now the only solution for the OS is to map inside its own virtual address space in this part, okay, of the P1's address space to map that physical memory, okay, like that. And now the OS will use VA in OS, okay, of course, for the P2 memories, which actually make access to the physical memory addresses, which make access to physical memory allocated to P2, okay, but they are somehow translated into virtual addresses of inside the OS, okay. So that's the only way in situations like that for the OS to make access to memory of other processes. But otherwise, being mapped inside each process address space, that makes very easy for the OS to have access to the process, the current process virtual memory. Okay, this one. I told you last time, very briefly, I told you that if we have the OS mapped inside the process, each process virtual address space, we could have some problems like that. Okay, so when the process is running its own code, so the CPU is running inside the process memory, so is running in user mode, so in the non-privileged mode. What happens if we have here a jump or a call or just a move using virtual addresses in this part of that process virtual address space, in the part where the OS is mapped? Is it possible or not? If it would be possible, then we have a problem. We had a problem because in that case, a process running in process mode could access the OS memory, which is not good. In practice, this is not possible because of some protection mechanisms which are provided by the CPU, okay, by the memory management unit actually. And that process is actually, and that mechanism, sorry, allows the OS to configure that part of the memory mapping table, okay, talking in terms of paging, okay. Maybe you remember that for paging, that table consists in more entries, each one for each page in the virtual address space, okay. So for the entries mapping pages in the OS part of that process virtual address space, so here, there is some flag, okay, which is, I know, set 1, let's say. I don't remember exactly if it's 1 or 0, doesn't matter, however. For all the other entries here, those flags are 0, and the CPU is inspecting when making access, when translating from a virtual address in its corresponding physical address, is inspecting that flag. And if that flag is 0, that means that it is accessible, such an entry, such a page, and the corresponding virtual addresses are accessible only in user mode. If that flag is, that bit is 1, that those entries and the corresponding pages are accessible only in kernel mode. So these entries mapping these pages, so this part of the memory, are marked as being inaccessible in user mode. And if an attempt like that is an access like that is attempted by a process running in user mode, actually the CPU checking that flag will detect that as a not allowed access and will raise an exception. Okay, so something like that could be blocked by the OS configuring appropriately that part of the mapping table. Okay, so just to be very clear, that when we map the OS inside the process address space, will not expose the OS to that process, actually to all the processes in the system. Still, if you are curious about this, I will not insist, at least for the moment, on this. Maybe you heard about vulnerability inside the operating systems. So there were some very important vulnerabilities discovered in many processors, including the Intel ones, which allows processes running in user mode to avoid the protection mechanism I've just described to you, a vulnerability which is called meltdown. Meltdown, if I understood that name correctly, is because that barrier here is melted, okay? And such accesses could be somehow performed. Meltdown is because of the out of order, so maybe the arrow in the other way, out of order execution of instructions inside the CPU. I suppose you know what I mean. So the CPU tries to execute more instructions in parallel, maybe not in the order they are given. In the executed process, and because of this, even if at some moment we could have a move, okay, which tries to make access to an operating system address, okay, moving its context in a register. Okay, the order of the operands is the other one, but doesn't matter. So just to understand that I want to make like this to have a memory leak, okay, from the operating system. So even if such an instruction normally is blocked because of the mechanisms I described to the configurations in the mapping table, because until that an exception is raised for such an instruction, some others are executed, okay? And so these others actually allows to use the contents of that memory in that register, and that affects the cache of the processor. Otherwise, the program execution is reverted, okay, is rolled back until that instruction. So all those instructions executed out of order are, their effect is made invisible for the program execution. So finally, an exception is raised, and the process could be terminated because of such an attempt, but the cache remains affected. And then an attacker, a process attacking the operating system, could inspect the cache and could deduce from the cache contents which was actually the value read or accessed from that address in the OS. Okay, so that just to give an idea about the meltdown vulnerability and the attack. Okay, so because of this vulnerability, which, pay attention, is not inside the software space, is inside the inside the CPU. This is in hardware. So in current operating systems, but not including HAL, in that case, so Linux, Windows, that picture is not exactly like that anymore. So when, for instance, when the process is running its own memory, inside its own memory, the OS is not mapped anymore here, or not entirely. Just few parts of the OS are mapped here. Otherwise, the OS is not mapped, okay? Such that when an attempt like that is performed by the process, such an attempt to not succeed, because if in that part the memory is not mapped, out of order execution doesn't work at all. Okay. Okay, so if you are curious, please read more about the meltdown vulnerability. In relation with this, you can also read about Spectrum. So that were the two vulnerabilities, important vulnerabilities, which were discovered in the modern processors, and this is because they're optimization mechanisms. Okay, good. Now coming back, in HAL we have something like that. Ignore the possible attacks which could be performed on the operating system, and keep in mind mainly the idea that such a configuration helps the operating system make access to the current process memory. Okay, good. I also told you last time about the fact that the virtual address space of a process is a sparse one, which means that just few parts of it are allocated. So supposing we have here the memory mapping tables, and here is the physical memory, the RAM. So now let's suppose that a process physical memory is not allocated in just one chunk, but in different. Okay, so these chunks could be mapped in different parts of the process virtual address space. Okay, like that. But what is important to understand is that not the entire virtual address space is mapped on corresponding physical memory. So actually the process is allocated just, you know, few kilobytes, tens of kilobytes, megabytes, things like that in the physical memory, exactly the amount of memory that process is using, okay? Not anymore. Even if virtually that process could make access to a large amount of memory, physically is allocated exactly at as that process needs during its execution, okay? So that leads to the virtual address space of a process having such gaps, okay? Such unallocated, unmapped areas. This is important to know about because when a process is running, let's suppose that here is the code, okay? Here is the code and we have move instructions making access to the data. We have call instruction making access to the stack, for instance, okay? These are the other parts of the process memory which are used when that process is executed. So if we have references like this, this could be translated, okay, to their corresponding physical addresses. So that works just fine. But if we have a reference to a memory like that, okay, a virtual address which I call invalid, then the CPU trying to translate such a virtual address to its corresponding physical address will find out here in the configuration of the memory mapping tables that such an entry doesn't exist. It's a kind of null, if you want here, okay? It's an invalid address. And the CPU will raise an exception when trying to make access to addresses like that. It's a kind of page fault or segmentation fault, okay? Generally speaking, is an attempt to access an invalid memory address, an unmapped virtual address, okay? If something like that is attempted when the process is running in user mode, is running its own and accessing its own memory, such an exception will switch the CPU from the process memory and code inside the operating system, and the operating system usually will terminate such a process. The operating system usually has no way to determine what should be there at that virtual address, such that to map it correctly on the physical address, okay, on its corresponding physical address. So normally it's not possible for the OS, and the only solution would be to terminate such a process. We'll see when we talk about paging, so or in the context of paging, that some page faults do not necessarily lead to the process termination. Some of the page faults could be because of the operating system delaying loading physical or the contents of a process inside of physical memory in order to save space in the physical memory. In cases like that, when is somehow the operating system fault that the memory is not yet mapped, the operating system, of course, transparently will load the required memory, the required contents in the physical memory. So we'll allocate necessary physical memory and we'll map the faulty page, okay, on the allocated physical space. Okay, so there are some cases when a page fault, an invalid memory access will not necessarily lead to a process termination. But generally speaking, okay, supposing that when we run a process, we run an executable, its entire contents is allocated physical space. So in a case like that, an invalid memory access will lead to process termination. The problem is, so this is something you have to deal with in your project. The problem is when, let me illustrate on another slide, when running a process, okay, okay, let me illustrate all the agents here, all the implied agents. So you have the RAM. So here we have the code of some process. Okay, that code is mapped where it should be using the memory mapping tables of that process. Okay, so like that. P1's code. Okay, now the CPU is running code inside that process, and that process makes a syscall. Okay, and let's take an example again, the same one. Reading from some file, FD file descriptor, indicating a buffer 10 bytes. That buffer normally should be in some data segment, okay, of that process. So the buffer's address, okay, virtual address in P1 should be something like that, VA P1. If something like that, such a parameter is given to the operating system, now the CPU will switch, okay, based on this system call here, in the operating system, letting the OS handling the system call. And now the system call is provided as the parameters of that system call, the file descriptor, the buffer's address, so a virtual address inside the P1's virtual address space, okay, and the number of bytes that should be read. And when now the operating system will identify the file, read the 10 bytes from the current position, and must store them in the buffers, in the process one's buffer, could use that address as it is, okay, because of the reasons I told you, because the OS is also mapped here. But what happens if such an address is invalid? So instead of pointing here, points somewhere here, okay, to an unmapped, into an unmapped area. Pay attention when the system call is called. So when this read is performed, the CPU running inside the process will not try to make access to that buffer, to that address, okay? That address is taken as an integer, is placed on the stack, or is placed in some register, okay, depending on the communication convention between the process and the operating system, based on what is called the calling convention, function calling convention, okay? So that value is, or that address is taken as a value and is not tried to be accessed inside the process. It is only given to the OS, and now it will be the OS trying to make access to it. And now if that address, such an address, is invalid, okay, the CPU trying to translate it from here to its corresponding physical address will find out in the mapping tables, in the current mapping tables, that it is invalid, is not mapped, and will raise an exception. The problem is now that the exception is raised when running OS code. And if the only decision to take when encountering such an invalid access is to terminate the process trying to perform that access, in that case is the OS which must be terminated, okay? So actually an access like this could terminate the operating system. So finally could crash the entire computer, which is not what we want clearly, because it's not the operating system fault that an invalid address was given here, but it's the process fault. And the operating system must never be affected by something wrong, which is done wrong in a process. The operating system must be protected by any such kind of an exception. If the process, for instance, tries to divide something by 0, okay, which again the CPU cannot perform, must not be the entire system to be crashed, but only that process, okay, to be terminated or to be crashed, as we used to say. If that process, for instance, is corrupted, as the CPU encounters some bytes which cannot be identified and as a valid instruction, okay, an invalid instruction exception is triggered. Again, must not be the entire system to be crashed, but only the corresponding process, okay? So similar to any other exception which must affect and or maybe terminate only the current process, this kind of invalid memory access exception must affect the current process and not the OS. The problem is that the OS in the context of that system call, okay, so running on behalf of the current process, is the OS trying to perform that invalid access, trying to perform that, this invalid access. So in order to not have something like that, before starting to use those addresses or addresses like that, the operating system must be sure that it will not get into an invalid memory access exception, okay? So in other words, the operating system must validate those addresses, okay? Now the validation includes the following conditions to be checked. The first one is to be sure that that address, it's not maybe exactly the order which is given to you in the HAL documentation, but maybe it's better for us right now to take them in that order. So the first condition would be to check if the VA in P1, which again, I'm sorry insisting for that, is the OS which will try to use it, okay? So if checking if this address is mapped. You have functions for that. You have functions for that prepared in your HAL. The idea is that such a function, such a checking, will go to the corresponding entry in the page tables and see them if they map something or not. Okay, if they are valid entries or not. Okay, that's the idea, but you don't have to care too much about this. There is a function. I don't remember right now its name exactly. It's a function which allows you to perform such a check, okay? The second condition to be checked, check if permission rights are okay for that VA. Why? Because, for instance, in that case, when the process tries to perform a read from a file and to store the read contents in a buffer, that's a write operation for regarding the memory. And checking the permission rights is to see if the process has the right to write something into that memory, supposing that it is a mapped memory, okay? It is a valid memory. But maybe because in the mapping tables, the operating system could also specify permission rights for a particular part of the process memory, being it in terms of reading, writing, or executing, okay? So normally for a buffer like that, permission for reading and writing must be allowed. If write is not given from some reason, for instance, it tries to write here in the code. So the buffer, by mistake maybe, is in the code area. The code is given the execution rights, but not the write permission usually. So in a situation like that, the write would not be allowed. Again, that must be checked by the OS before trying to perform that operation, okay? Again, there is a function which allows you to check permission rights like that. If I'm not wrong, if I remember correctly, the same function, okay, allows you to check both such conditions for a virtual address, checking if it is mapped and in the same time if the needed permission rights are allowed. And the third condition to be checked is because of this aspect. Let me illustrate it here. Is because in the process virtual address space, okay, the OS is also mapped. And now if this VA of P1, okay, this one which normally should go to a buffer inside the process memory, if VA actually goes inside the operating system part, we have a problem. Pay attention. And sorry for insisting on some aspects. Is not the process trying to make access to that address, because if a move, for instance, is tried here in the process when the process is run, that access is not allowed because of the reason, the mechanisms I told you about. But that address is given to the OS, and is the OS trying to make access to that address. And now the CPU is running inside the OS and is running in kernel mode, and all those checking in the mapping tables would succeed, okay? Will show the CPU that that part of the memory could be accessed by the OS, and the CPU is running inside the OS, okay? So normally the OS is allowed to run something here, but if it does something like that, if it did something like that, then the OS running on behalf of P1 will write inside its own memory, maybe changing some data structures or something like that, which is not good at all, okay? So that virtual address must be in that part of the process, sorry. In that part, okay, of the process virtual address space, and not going over this limit, okay? So that's the check, the third condition. Check if VA P1 is less than some limit of OS, okay? That's the limit of OS. So the virtual address from where the OS is mapped, okay? So must be like that. If it's not, if it's equal or greater than this limit, it should not be allowed. So you could make checking, you should or you must make checking like that on all the system call parameters which are virtual addresses, okay? You are also told in the HAL documentation about some other way to deal with these conditions, okay? I will not insist on that. Is to allow a page fault to occur and to make the the needed checks there. Doesn't matter for the moment. Somehow, even if it is said in the HAL documentation is not the optimum way to deal with situation like that, I would recommend you to do like this, because doing that you'll understand better the reasons of making checkings for like that for such parameters, okay? Of course, you are free to choose any solution you want, okay? But that's my recommendation. There was another aspect I wanted to tell you about. Just give me a few seconds to try to. Yes, the other aspect you are said in the HAL documentation about validating parameters like that, okay, which are virtual addresses, is to pay attention that sometimes, and it's a good example here, it's not only that address which must be validated. Why? Because if we look at the read functionality, it's not only the byte of this address which is accessed, but actually more bytes are accessed starting from that address. In our example, starting from this VAP1, okay, where the buffer is supposed to start, the OS must store 10 bytes, or maybe 100, or maybe 1000, or maybe 10,000 bytes, okay? Let's take this number. If 10,000 bytes must be read from the file and stored in the process address, in the process memory, starting from this address, sorry, actually that buffer could be as long as this, actually being or traversing or covering more pages, okay, talking about paging. And the memory management granularity for paging is the page. So the OS and the CPU at one moment check if a page is valid or not a byte, a page. A page is usually a 4 kilobytes. So a page size is 4 kilobytes. That's the most common value. 4 kilobytes is 4096 bytes. Okay, so when we start, the OS starts checking the buffer or running in the buffer, maybe it will make access to one page, to the second page, third page, and so on. Okay, in our case is 10,000 divided by 4096 is about 2 or 3 pages, maybe, which must be accessed. Okay, for storing the read bytes in the process memory. So it's not enough to check only if this VAP1 is okay from this point of view. Okay, is good, because that only refers to the beginning of the buffer, to the first byte in the buffer. But maybe those bytes here should not be anymore okay. Maybe that part of the buffer could be in the OS part of the memory, or could be not mapped, or could be not given the necessary permissions. So actually, specific to each system call, you have to check the entire memory which will be accessed by the operating system when handling that system call. In that case, for instance, you have to take into account also that third parameter. So starting from this address, you have to be sure that all the addresses, VAP1, VAP1 plus 1, so VAP1 plus 1, VA in P1 plus 2 until VA P1 plus 9999, so 10,000 minus 1, all of those addresses are okay, are mapped, are not in the OS, are given the necessary permission rights. Okay, if you take into account paging and the page granularity, you could easily see that you don't have to check all those addresses, but only actually the beginning of the buffer and then the bytes which are at the beginning of each page. Okay, it's enough to make that check, because a page is entirely mapped or not, is entirely given the necessary permission rights or not. So the granularity is the page, okay, is not a sub page. And that's why you could optimize that in some way. But again, I'm not necessarily interested in optimizations like that. You could check each such an address one by one, just to understand precisely what and why you have to do something like that. Okay. Let me keep you 1 or 2 more minutes, and then I will give you the break, because there is another aspect you have to keep in mind about this. Let me show you. So in this context of validating, so the context is validating syscall parameters which are virtual addresses. Okay, this is what we are interested in. There are 2 kinds of such system calls. Let me give them as examples. For instance, if you have in terms of file create, and the other one was the file read, the read I showed you before. For file create, you are given as the only parameter a pointer to char, which is a virtual address. Okay. For the read, we saw that we have a file handle, and we have a virtual address, which is the address of the buffer. Okay, a buffer is here, and we also must take into account the number of bytes which must be accessed. Okay, or the number of bytes which must be accessed inside that buffer. Okay, so this is that 10. So this is one kind of system call where you are given the starting virtual address and the number of bytes which must be accessed starting from that address. Okay, and the way to validate the buffer is the way I showed you before, going one address after the other in a kind of a for, because you know which is that number of bytes which must be accessed. If you have system calls like that, where you are given a pointer to a null terminated string, okay, so we also have here a kind of a buffer, okay, which is the name of the file, but what we don't know here, comparing with this case, is the length of the buffer. Here we are given the length, here we are not given the length, but what we know is that that buffer is terminating with a 0, with a byte which is 0, okay? In that case, the validation must take into account that convention. So we must start from this address, VA in P1, and take one byte one by one until we encountered one which is null, which is 0. Of course, firstly, we have to validate the byte and then check its value. If it's not 0, goes further. Validate it, check if it's 0. So actually, take one by one bytes until we encounters a valid one, so one at a valid address, and whose value is 0. Everything is clear in relation with this aspect? Okay, if it is, let's take the break. It's 4 before 9, so we see again at 6 past 9. Okay, so we have a 10 minutes break. Thank you. Okay, I am back. Let's resume it and let's go on. Okay, so I try to explain you something that you have to deal with in your project. On one hand, on the other hand, it's something that the OS must deal with in practice. However, just to make a parenthesis here and to talk about some security aspects, okay? Maybe that will be finally the only way to talk about aspects like that, because maybe at the end I will not have specific time for this. So actually, that's something that we'll also talk about, and you'll find out on the slides a question raised in relation with this. With a user stack, okay? But for the moment, let's note that in the context of handling of system call, called from a process, and that process giving the operating system a virtual address inside that process, okay? So the OS, you noted, could make all the checks to be sure that that virtual address or the entire buffer which must be accessed is inside the process memory, is not in the OS part, okay, of that process virtual address space. So somehow everything seems to be safe from the operating system point of view. But the problem is, let me illustrate that on another slide. So we have that process. So let me separate the two parts. So we have a virtual address which points somewhere here to a buffer which is mapped. Okay, so everything is fine. So let me illustrate it like this. So here is the OS. That's the mapping tables, memory mapping tables for this process. Here is the physical process, the physical memory, sorry. Okay, so that memory is mapped on some physical memory. So it's just fine. But we are in the context of the CPU running inside the operating system handling a syscall. Okay, a syscall which was executed, was called by the process. And that VAP1, okay, is the one accessed by the operating system. Okay, again, it leads where it should be. The problem, or one problem, could be that that address, which is in used by the OS handling the system call, belongs to the process space. Now, we could have problems if we have multiple threads inside that process, because if we have multiple threads, such a CPU will run in the context of one particular thread, okay? Generally speaking, is running in the context of that process, but in particular is running, thread 2, okay? Which means that the CPU running that thread was switched from the user space in the kernel space. The corresponding thread, T2, is suspended in user space and OS is running on behalf of it in kernel space. The OS in the context of that thread is trying to make access, is making access actually to the that process address. In the meantime, some other processors, okay, CPU 1, CPU, CPU 3, and let's name it CPU 2 for making association with this thread 2. So while CPU 2 is running OS code, the other CPUs could run in the same process user code. And those threads could also make access to that memory. Okay, so the OS is making access to the memory, but concurrently, in the same time, in parallel, some other threads in the process makes access to the same memory. Okay, let's ignore that this could lead to race conditions and maybe that could lead to inconsistent results, things like that. Maybe that could be solved imposing some locks, things like that. The problem is now, or the problem, so the challenge we want to talk about is from the security perspective. Is the OS protected in situations like that? The answer is not, or not necessarily, because while making access to that memory, I know reading from it or writing to, maybe reading, when reading from it, okay? So reading actually reads information which may be used by the operating system, okay, to influence its execution flow. If such information are affected while being read by the other threads in the process, those threads maybe could be untrusted or should be untrusted. Everything in user space actually should be taken as untrusted by the OS. Because the OS cannot control what happened in user space. User could run anything, okay? The OS must protect itself from any mistake, any invalid access or things like that, which is tried to be performed by the OS, by a process, sorry, okay? So in cases like that, while the OS is reading some process memory, while other threads, the process itself is modifying that memory, could influence in a bad manner the operating system, okay? So that's something which should and raise some questions, some warnings about situations like that. This is called in the security world double fetch vulnerability, because the operating system, let's take the example with the file create, okay? File create, which, as I told you, is given a char pointer, which is the name of the file, okay? The operating system knows that here is a null terminated string, maybe allocate some memory to store it here, okay, to perform a copy. I know, from some reasons, doesn't matter precisely if that's exactly the way you'll handle this file create. It's a possibility, okay? It's just an example. So maybe the OS wants to allocate some internal buffer to copy the process memory's contents from here inside its own buffer. Being a null terminated string, the OS doesn't know from the very beginning which is the length of that, okay? So must be used, I know, string length or goes byte by byte to identify the 0 here, okay? So the first fetch, the first checking is when the operating system is accessing that memory, so fetch it, okay, look at it, to identify something and sees some state of that memory. For instance, identify the the offset 10. After that, so after using, in our example, string length to find out that the length of that null terminated string is 10, after that using a string copy, okay? String copy, in between allocate 10 bytes in that internal buffer and use string copy to copy this string into this string. But in the meantime, so after calculating the length of that buffer and correspondingly allocating the length of that buffer, allocating that buffer of the same length, in the meantime, the process remove that and move it somewhere else, okay? At a further offset, at the larger offset. And now when the string copy is performed, the string copy also checks for the null terminated byte, the 0 byte, okay? And now which is moved. So which means that string copy will overflow that buffer, okay? Instead of writing only the allocated bytes, it will run more them, overwriting some memory not allocated memory inside the operating system, okay? So the second time, the double, okay, double fetch, the OS is fooled to perform something which does not correspond to the initial fetch, okay? Which is something which could be really bad for the operating system, okay? So moving that 0, okay, competing with what the OS performs here, you could see could influence in a bad manner the operating system execution, which is really not good. It's really not good. Something like that should be avoided, okay? Now, there are some possibilities to, instead of using string copy, for instance, use, I know, string n copy to copy maximum 10 bytes, okay, or something like that. But it's something you have to, or we have to take care of, or to take into account when we design an operating system and take decision in relation with parameters like that of system calls, addresses, okay? Addresses in the user space. So if you are curious, again, you could read more details about such vulnerabilities, such security aspects, double fetch one, okay? In general, however, just to have a sort of a conclusion here, is a good idea for the operating system while handling system calls to not use memory in the user space, to be sure it has its own copy of that memory, not necessarily copying it, okay? Maybe, I know, mapping in its own virtual space these addresses, okay? Because that address is not only the contents which should be checked, could be changed by the process. The virtual address itself could be unmapped, for instance. So using some mechanism, deallocates in the memory, for instance, that process could make the buffer invalid, okay? Not only changing its contents. So it's a good idea to make a safe copy inside the operating system of everything the OS must use when handling a system call, okay? So making a safe copy of the process memory inside the operating system, use that copy, that safe copy, which cannot be affected by the process while the OS is handling the system call. And when the system call handling is finished, move back the data in the user space, okay? Of course, such a mechanism will consume more memory than in the other situation, but you have to balance, okay, optimization, saving memory with security. Okay, sometimes maybe you have to unbalance, okay, the decisions for having a better security, to have a safer operating system. Okay. Good. That was all about handling system call parameters, which are virtual addresses. Okay, you don't have to deal with double fetch in your OS. Just to have an idea about this, you only have to validate if those parameters, those virtual addresses, are good from the perspective I told you about, checking all those three conditions. Okay. So on the slides, okay, you are told about this somewhere. Doesn't matter exactly where. However, at one moment here, so I skipped all these aspects, but I will go back to them at some moment. Immediately, actually. On the slides. Here is where we have discussions about system calls, how the system calls are performed. It's something that I will let you take a look by yourself. System call layers. That's another aspect, yes, which I should talk to you. Pointer argument validation. Okay, here is where is given details about the aspects I told you about. Now, the next aspect you have to deal with in your project is that about user space. Yes, user space stack. So the idea is that when you run a program, imagine that that program is launched using a command line interpreter. Okay. Of course, in real operating systems, you could use a user interface, but finally, things happens like this. Let me take another board here. So here we have the user interacting with a kind of a shell, so interacting with a current process. This is process P1, and here you have the OS. The way to launch another application, okay, is interacting with this process, giving a command or things like that, user action, and that process will ask the operating system. So actually we have a syscall, dedicated syscall, which should be provided by the OS, a syscall which is kind of create process, okay? Such a system call should be given. The operating system handles that system call, allocates internal data structures, allocates memory the way I told you about, okay? And finally, that results in a new process with all its resources allocated by the OS, okay? That's the parent, that's the child, that's the process P2, process P1, that's the parent, and that's the child, okay? But you know that when you run a new application, when you create a new process, especially in cases you write commands in a command interpreter, you could give that new process parameters. So the same program, the same executable could be run multiple times, but with different parameters. Those parameters are what are called command line parameters, because usually they are given in a command line, okay? So running this P2, for instance, let's suppose that's an executable in the current directory, P2, let's call it P2x just to be very sure that it's an executable. You could give it parameter 1, parameter 2, parameter 3, okay? Okay, these are given, such a command line is given to such a shell. Maybe the shell is able to specify all those parameters in the system call, which calls the operating system, which switches in the operating system. So the OS knows that the new program is called P2x and its parameters are P1, P2, and so on. Okay, all these are strings. So null terminated strings. Okay. And now let's see how this new process, P2, could make access to those parameters. If we write such a program in C, okay, maybe you remember that in order to have access to the command line parameters, these are specified, or these are given to the program as parameters of the main function, okay? And the main function has a signature like that: int, an integer parameter, which is used to be called argc, argument counter, and an array of strings, so in terms like that, which is used to be named argv, argument vector, okay? The argument vector, argv, so that's a pointer, okay? Firstly is a char pointer, argv, so this takes this part, and the elements for this part is a pointer, and the elements in that address are pointers in their turn, okay? So each element is in its turn a pointer, a char pointer to a null terminated, so that's a pointer, and another pointer to a null terminated string, okay? To a \0 terminated string, okay? That's argv0. Then we have the same way argv1, and the number of these pointers here is argc, okay? Argc actually correspond to the number of items in the command line. In that case, 1, 2, 3, 4, okay? So in that example, argc is 4, so we could make access to argv0, 1, 2, and 3. Okay, argv0 is the name of the program, argv1 the first parameter, argv2 the second, argv3 the third parameter, or in other words, the fourth word or item in the command line. Okay, that's something that I suppose you know about. So For that program, that's the way. So when it starts running in its main function, okay, I mean thinking machine language, okay, or assembly language here, the main is like calling that function with some arguments. And the calling convention, okay, for C programs specifies that the function's arguments must be given in some registers, or mainly most of the time on the stack. Okay, so that main function expects, when being run, to have its arguments argc, argv, and the contents of argv on the stack. Okay, so that's why when handling a process or create process or process create system call and allocating memory for the new process, for the child, and because is the OS allocating the stack of that process, is the OS which must prepare the stack such that the main function to find out its parameters on the stack. Okay, so those parameters do not occur there, I know, magically. They must be placed there by the OS being the one allocating memory for that process. Okay, all the other parts of the process memory, the memory of that process memory contents are taken from the executable. Okay, the code is taken from the executable. The data, the initialized or uninitialized data, is taken from the executable, but the stack is a memory allocated dynamically, okay, by the operating system, and normally having no initial value, initial contents. Still, because the OS knows that a process starts by executing its main function, okay, the OS must prepare the stack for the main function. Now, let me take a parenthesis here, because maybe you already know, from your own experience, or at least from reading HAL documentation, you know that it's when a new process is started, is not the main function which is actually the first one which is called. Okay, if you took a look at the HAL documentation and in HAL code, especially how the user applications are built, so I will come back to that board a little bit later. Let me think a little bit. Let's illustrate like that. So that's a process, okay? A process, a program, doesn't matter how you call it. So in the process, we have the code area, okay? In the code area, the main function is somewhere here, but it's not the first function to be executed. There is another one, and I don't remember exactly how it is named in the HAL. Let's call it like that, start, okay? If we take a look in the executable, so P2exe, okay? So that's the executable file. In its header, there is an information which is named entry point, okay? The executable contains the code, so that code is actually loaded by the operating system from the executable file inside the memory. So that's the memory of a process, okay? And the header of the executable specifies for the operating system which is the entry point to start that process execution. And usually the entry point is not the main function, is another one, okay? Doesn't matter exactly how that function is called, could be called however you want, actually is an address which is given there, okay? Is not a name. So the operating system knows from the executable, and the executable was generated by a linker, okay? A compiler and the linker, okay? The linker is the one establishing the structure of the process memory and establishing the entry point. Of course, is the application developer, which is configures the linker. Okay, usually it's exactly like that in your case. So your Visual Studio projects are configured, okay, to specify which is the entry point in an HAL application. Finally, it's in the executable where the entry point is specified. So what is interesting to note here is that is not the operating system decision, is the linker decision, that the operating system must comply with those executable specifications. So it loads the code and searches for the entry point. That's the entry point. In the entry point, main is called with the expected arguments, argc, argv. Argc and argv actually are exactly the parameters of that function. So imagining that function not in assembly language but in C, so this start or the entry point function also should be called with argc and argv. Okay, so the first function, okay, I place it between quotes. I explain why immediately. The first function to be called is this one, but actually I placed it between quotes because it's not called. The operating system prepares the CPU, okay, configures the CPU to start running from this point. It's not a real call before performed by the CPU, so it's not a call, okay, it's not a call, it's just the instruction pointer configured to point there, and then the CPU is led to run code at that, starting from that address. Still, when the CPU starts running code here, the compiler generates code here as if the start is a function. So if you take a look in your HAL project, in your HAL operating system, but pay attention, that's in the user space area, okay? It is in the user applications, it's not in the kernel. So if you take a look at how the user applications are generated, you could find out that the entry point is declared as a function. And the compiler generates code for a function as if it was called from somewhere else, which means that the stack structure should be exactly like for a function. Sorry, as if for a function which was called from some other place. And the structure of the stack when a function is started looks like this. Arguments, okay, arguments of that function, then the return address of that function. Sorry, I'm in such a hurry that I write awfully. So let me write it again. So on the stack, the start function, the way its code was generated by the compiler. Okay, so the start function expects the stack to be in a way in a structure like that, to have the arguments, then the stack grows, okay, in that way. Okay, just to be very short. So here is a kind of 0 small addresses, and here is larger addresses. Okay, then so arguments, more arguments. Then when the call, supposing a call was performed for going to that function, then we know that the CPU automatically placed here the return address. So the return address is expected to be here. Then if you take a look of how the code for function is generated, you'll easily note a kind of how it's called, a preamble, okay, of all the functions, which saves the RBP register, base pointer, RBP, sorry, okay, and maybe some other registers, but that's the way to do usually. And here we have the local space for local variables, okay, and here is where the new base pointer is established, and here is where the RSP is now after reserving space for local variables. Okay, so that's the regular structure of the stack, which is expected to have when a function starts being executed. Okay, what you are interested in, because the way the function is executed, saving the RBP, reserving space for local memory, is in code, so that's dynamically established. What you have to establish is this part. Okay. And here is now coming back to that particular function, the start, which expects its arguments to be an integer and the pointer. Okay, you have to establish that structure on here. Okay, I'm not sure I have to go back to that picture anymore. Only maybe to remind you that these are the parameters. Okay, maybe we could take now another board here. So the operating system, maybe let me go back to that one. So we are in the context where you have to handle a create process, okay, system call. So a new memory is allocated for a new process for the child. A stack is allocated, and the stack structure must be established by the operating system, actually placing those parameters here in some way. Let me show you exactly how this is for your operating system. Firstly, you are told that for the operating system, okay, running in the context of the parent, so the OS is running in the context of the parent, but it allocates memory for the child, and the stack of the child is in the context of the child. So the OS handling the create process has no way to directly access the stack. Okay, it's something that I've already told you. So the only way for the OS working with a stack in the child virtual address space is to map the corresponding physical address. Okay, so this goes here physically in the RAM. Okay, here is the physical stack, and the OS, okay, in this part must map that address also in its own virtual address space. Okay, so the virtual address space in the child for the stack, and the OS must establish its own in the OS virtual address space for the stack of child. Okay, so you have a function to do that. Please read about this in the HAL documentation. So once the OS has access using this VA OS, okay, to the stack, the idea is how that stack should be configured. I used to illustrate the stack in the opposite way most of the people do. Okay, so here is the 0. Okay, the small addresses. Sorry for writing such awful. So small addresses, and here are large addresses. You know that a stack goes from small. Oh, sorry. No. Sorry. I said wrong even on the previous slides. Please, if you know that I make mistakes, please correct me. Okay. So here are large addresses and here are small addresses. Okay. So here is the 0. So the stack grows from large addresses to small addresses when we perform a push. Okay, that's equivalent with decrementing the stack pointer register. Okay, just to be very clear, I used to illustrate the stack like that, in that direction and not the other, just because I imagine that when I push something on the stack grows in this way, okay, at least in real life. Now, some memory is allocated for your child stack, okay? Normally, I know a page could be, or if I remember correctly, there are 8 pages or something like that in HAL. However, initially, the stack pointer is at the basis of this address, okay, of the largest address of all these pages, okay, here. And nothing is normally on the stack. But when the start function, okay, is executed, the entry point, okay, it expects on its stack to have an argc and an argv, okay, and also that function supposes that it was called from somewhere else, and on the stack the return address exists. Okay, so let's start from the top of the stack, how the stack should look like finally, okay, starting from the top, where finally the register, the stack pointer register should be. So on the top of the stack should be a return address. That's called in the HAL documentation a fake return address. Why? Because I told you the start function was not called from was not called at all from anywhere, but the CPU was configured to start executing that function directly. Okay, so having no call from somewhere, logically there is no return from that nowhere. Okay, but the other reason the function execution will work correctly, because if you will take a look at the start function, you'll see that a return. Okay, the return normally looks for a return address and tries to jumps there to the return address. The reason there will be no return there, even if the return instruction exists, is that because the start function, the entry point function of a program, looks like this. Call the main with argc and argv, and then call the exit. Okay, in HAL it's called process exit, but doesn't matter. Exit with some termination code. That exit is a system call which goes inside the operating system and informs the operating system that that process terminates. And if that process says to the operating system that it terminates, the operating system decision will be to remove the address, the memory of that process, to destroy, to terminate that process, and never return the CPU from the OS in the memory of that process. So never resume the execution of that process. So actually that return should never and is never reached. Okay, that's why that return address, which is expected to be there, is actually never used. That's why it's called a fake return address. Okay, so when the start function is starts execution, the stack should have on top of it the return address, such as if that function was called. Then here we should have argc, which is a number, in our example was 4, and an argv, which should be a pointer pointing somewhere in the process memory. Where? Could be anywhere some memory is allocated, but the easiest way to deal with that is to point on the stack, because the stack is a memory allocated when the process starts by the operating system, when the process is starting. So argv should be configured to point somewhere on the stack. Could point immediately here, or could point below, or doesn't matter. That depends on how you want to configure the stack. But obviously you not want to lose space here. Okay, maybe argv will point immediately after that position. Okay, what should be here? Remember, argv looks like that, an array. So that's the way to look for to be argv, an array of pointers. Okay, so is an array, is a contiguous memory. Okay, so having 4 elements in our case. Okay, that's the argv0, argv1, argv2, argv3. There is a convention which says that if we have argc elements, we should add an additional one which must be 0, actually the null pointer, as a kind of a sentinel. Okay, it's just a convention. you could follow it or not. But let's say you follow it. Okay, here we have a null, that's the sentinel. Here we have argc elements, and the argv points to the first element. Okay, maybe here. That's the way to configure that element on the stack, that RV, 2 point here. Of course, you have to reserve that space. And then you must configure the elements in argv, argv0, which is again a pointer, where that pointer should point anywhere in the process memory. But again, the easiest way to do is to point on the stack. Okay, let me increase a little bit the stack. So this one should be configured to point here. What should be here? Here is p2.exe, okay, because that was the name of the program I took as an example. Terminated with 0. That's the string, the null terminated string, which contains the name of the program, p2.exe. argv points also somewhere here. This is p1, 0, okay, vector 0. This the first parameter, and so on and so forth. The second parameter, the third parameter, all of them points somewhere on the stack where the strings which were given to your program were stored. Okay, so normally once you allocate your stack, so initially the stack pointer is here, you should start from here and go in the opposite way which I described to you. I described the final structure of the stack, but when you create it, the easiest way to do is to go in the opposite way. Or maybe you could compute all that step, all that space, sorry, which is needed, and start from here and go in the opposite way. Okay, so computing all the needed offsets on the stack. That depends on that's your design decision. Okay, but finally, on the stack, you should have this kind of information. Okay, so you should have the strings which are taken from the command line. Then you have the array of pointers to those strings. And then you have to have the argv, so the pointer to this array, and the argc, which is the number of elements. Because HAL runs on the 64-bit architecture, you have to take care about a little bit more than that, because the calling convention supposes that the function, the first four arguments of a function are given in registers, but if you have more than 4, they are also on the stack, but they are on the stack considering also reserving also space for the 4 parameters. That's why actually on the stack, even if you have only argc and argv, or you need only argc and argv, you have to reserve space for 4 parameters. Okay, that's called in HAL the shadow space on the stack. So I will let you read about this by yourself. Finally, is you have to prepare the stack for looking somehow like that. Okay, it's not difficult once you understand the reasons of having that. What I explained you here, okay, is how a program starts, how a program calls the main, so it's not the main, the first function to be executed, how that function also calls exits, which means that always your program terminates with an exit, okay, even if you use it or not in your main function, and how the start and the main arguments actually goes on the stack. Actually, you are not preparing on the stack arguments for the main, but you are preparing arguments for the start function, for the entry point function. Okay, let's not abuse of your time. So let me stop here. Let me give you the password for today's lecture. Okay. Sorry. Here is the password. Please use it for for marking your presence. So it's or there are only small letters. GAS MGZ. Okay, that's all from my point of view. Thank you very much for attending that lecture. I hope that you learned interesting things, and maybe you clarified some things that you've already read about in the HAL documentation. Any question you have in relation with you have to do in your project, or in relation with what I present to you, please feel free to ask me on the Moodle forum, on the Teams forum, or just write me in private on the Teams. Okay, thank you very much. Wish you all the best and see you next time. Bye bye.
Thank you. Have a nice day.